Hello my dear students, in this lecture we are going to classify stresses. Now basically stresses are of two types. Stress is classified into two types. That is, number one is normal stress. Normal stress is also called perpendicular stress. Perpendicular stress, and it is represented by letter sigma. It is represented by letter sigma. Now second is shear stress. Shear stress is also called tangential stress. It is also called tangential stress, or it is also called parallel stress. It is also called parallel stress, and it is represented by letter tau. Shear stresses are represented by letter tau. Now, whenever load applied on the component is normal to the area, then it is normal stress. That is perpendicular to the area, then it is normal stress. And if load applied on the component is parallel to the area or tangential to the area, then it is shear stress. Now again, normal stresses and shear stresses are classified into again two types. That means there are two types of normal stresses. That is, number one is indirect normal stress and other is direct normal stress. Direct normal stress, direct normal stress, and other is indirect normal stress. Indirect normal stress. Similar to these, shear stresses are also classified into direct shear stress and indirect shear stress. But first we will classify normal stresses. Now, direct normal stress. Direct normal stress again classified into two types. That is, number one, tensile stress or tension stress, and number two, compressive stress. Number two, compressive stress. Compressive stress. Now see, let's say if I consider one element, let's say this is a component, and for this component, let's say this is the area, let's say this is a hatching area on which force is applied, right? On this area the force is applied, P, on this area. Then see here, the force is normal to the area, the force is perpendicular to the area, therefore stress will be normal. And force is tensile, therefore it is tensile normal stress. It is equal to P by A, and tensile stresses are considered as positive stresses. Now again, if force is applied compressive to the area, if force is applied compressive on the area, let's say this is the area, on this area force is like this, force is like this. Now see here, force is perpendicular to the area, therefore stress will be normal stress. And as the force is compressive, it is compressive normal stress equal to P by A. And for calculation, compressive stresses are considered as negative stresses. As here force is directly applied on the area, therefore it is called direct normal stress, right? Tension and compression are the types of direct normal stress. Again, in indirect normal stress, the example is bending stress. Example is bending stress. Bending stress is indirect normal stress. Now see, on any element, if bending moment is applied, let's say if component is bending like sagging, this is a sagging bending, right? This is a sagging bending shape. Smiling means sagging. See, beam is bending like this, and if I draw human face, it will be smiling face. It is means sagging bending moment. Now for this sagging bending moment, this is the axis of beam. Let's say this is the axis of beam, and bending moment is applied like this. If bending moment M is applied like this, then only component will bend like this. Now here, in strength of material, you have seen that on neutral, on axis, this is the axis of component, on axis there will be no stress, there will be no bending stress. That means the length of axis before bending and after bending is same. As the length is same, there is no stress. If tensile load is applied, length will increase. If compressive load is applied, length will decrease. And if no load, then length will remain same. Now see, upper fiber, above axis, if I consider element, then length is decreasing, means there will be compression bending stress, compressive bending stress. And if I see bottom fiber for this type of bending, then length is increasing, therefore there will be tensile bending stress. There will be tensile bending stress, means bottom fiber is under tension means positive stress, upper fiber is under compression means negative stress. Now for this bending moment M, you have seen bending stress magnitude. That is how to find bending stress. That is by flexural equation. It is also called flexural stress. Bending stress is also called flexural normal stress. Flexural normal stress. Flexural normal stress is called bending stress. Now, for this flexural or bending action, what is bending equation? M by I is equal to sigma B by Y is equal to E by R. This is a bending equation. This you have studied in strength of material. And here M is applied bending moment or design bending moment. I is area moment of inertia, area moment of inertia. Sigma B is bending stress induced in the component. Y is distance from the neutral axis, and E is Young's modulus. R is radius of curvature. This you already seen in the strength of material. Here I am only revising the things. Now again we will classify shear stress. Now, like normal stress, shear stress is also classified into direct shear stress and indirect shear stress. There are two types. That is number one, direct shear stress, and number two is indirect shear stress. Indirect shear stress. Now, in direct shear stress, force is directly applied on the area. Parallel force is directly applied on the area. Let's say if I consider one element, let's say this is a component, and for this component, this is the area on which force is applied. Let's say it is fixed at bottom, and on this hatched area, this is the area. On this area, if force is applied like this, if force is parallel to the area, then because of this applied force there will be shear stress because it is parallel to the area, and stress is nothing but force divided by area. Now this is a shear stress, right? Now directly force is applied, hence direct shear stress. Now again indirect shear stresses. Indirect shear stresses, there will be two types of indirect stresses. Now number one is due to torsional indirect shear stress. Torsional indirect shear stress due to torsion. Let's say if I consider one element, torsion is for circular shaft. If I consider one circular shaft having circular cross section, and if on the shaft torque T is applied, this T is applied torque. Because of this applied torque, if I consider one element in the component, see torsion is like this. Because of this applied torque, there will be torsional shear stress tau. Now, if I consider element, this small element, consider this small element. See, on right side of vertical plane, there will be torsional shear stress like this. For this tau, there will be equal and opposite tau. Now, as these two taus, that is two shear stresses, are creating couple in anti-clockwise direction. See, they are creating couple in anti-clockwise direction, or they are trying to rotate the object in anti-clockwise direction. Hence, to balance these couples, there will be clockwise shear on horizontal plane. There will be clockwise shear on horizontal plane of same magnitude. For action, there is equal and opposite reaction. No? Means this clockwise shear is balancing the anti-clockwise shear or anti-clockwise couple. This is the torsional shear stress, right? Now again, if you have seen in strength of material that what is torsional equation? T by J is equal to tau by R is equal to G theta by L. This is a torsional equation. Here T is applied torque, J is polar moment of inertia, tau is torsional shear stress, R is radius of shaft, G is shear modulus, that is modulus of rigidity, theta is angle of twist, and L is length of shaft. These notations you have already seen in strength of material. And due to torsion, the stresses are torsional shear stresses, indirect shear stress, right? Again, flexural shear stress. Second type is flexural shear stress. Flexural shear stress. That is the stress due to bending action or flexural action. Now again in a flexural shear stress, you have seen that due to bending loads, you have drawn shear force diagram, you have drawn bending moment diagram. From bending moment diagram, you can calculate bending stresses, and from shear force diagram, you can calculate flexural shear stresses. There, in strength of material, you have topic flexural shear stress, and formula is F tau is equal to Fa y bar divided by Ib. This is the formula, right? Tau is flexural shear stress, F is shear force at that cross section area or at that location, A is area above or below the fiber, at which fiber you have to calculate from this fiber area above or below of the fiber. Y bar is distance of the centroid of area from the neutral axis, I is moment of inertia of the entire cross section, and B is width at the section. This already you have seen in strength of material. This is how we can classify the stresses. In strength of material, you have studied direct normal stress, indirect normal stress, that is bending stress. Again, you have studied direct shear stress, you have studied torsion, you have studied flexural shear stresses. But in machine design, all the stresses are acting together on the component. All these type of stresses, that means there will be one normal stress also, or there will be two normal stresses on the same component, and there will be shear stress also on the component, or there will be torsion also on the component. Means there will be, again there will be, let's say it may be a combined bending and twisting problem. That is, there is bending moment is also acting on the component, and torque is also acting on the component. For such type of combined loading, we have to design the component, and for these combined loading, the calculation is done in complex stresses topic. Again, here we will see basics of complex stresses, how to find complex stresses, how to find principal stresses. That also basic we will see in machine design, but this in detail you have studied in strength of material. Thank you, students. In next lecture we will see if direct normal stress and indirect normal stress is acting on the same component, then how to combine them together.